So welcome back to the afternoon.
Yeah, no.
Oh,
Is this one? Oh, it was.
what's it? Okay. So welcome to the afternoon session. Oh, sorry. Welcome to the afternoon session. It's a pleasure to announce the talk of Christina Escher on non-negative curvature and torus actions.
Thank you. Well, I first would like to start by thanking the organizers for the invitation and also for putting together this whole workshop. You know, it's always a lot of work to put together a conference, but especially during a pandemic. So thank you. Okay, so I would talk about non-negative curvature and torus actions. And let me say from the beginning, curvature here will always be sectional. So when I talk about curvature, it will be sectional curvature. And all of this is joint work with Xiting Dong and Catherine Searle. Xiting was a PhD student that Catherine and I co-advised. So, and any questions you can ask Catherine. So. Okay, so let me give an overview. So of the talk. So I will start with a basic introduction to positive and non-negative curvature. So all of my curvatures will be bounded below, and symmetries. I will talk about the maximal symmetry ring conjecture. And then our main result is a classification of isotropy-maximal and almost isotropy-maximal actions. I will define all of that and state the result. And then I will sketch the proof of our main result. Okay, so let me start with the positive sectional curvature. So in general, the setup is we have a Riemannian manifold with a metric of either positive or non-negative sectional curvature. And the question is, what kind of restrictions does that impose on the underlying topology of the manifold? So interesting part here is that even though we have very few topological obstructions to a manifold admitting a metric of positive sectional curvature, we also know very few examples. So I wanted to just start with some examples. So if we assume that we have a closed Riemannian manifold simply connected with a metric of positive sectional curvature, and if the dimension is high enough, so if n is bigger than 24, the only known examples we have are spheres, complex projective spaces, and quaternionic projective spaces. There are some examples in lower dimensions that are different from that, but for n bigger than 24, that's it. Now, in contrast, for non-negative sectional curvature, we do have a lot more examples. So we have the same setup. The manifold is closed, simply connected, and now curvature restriction is now negative. We have a wealth of certainly many more examples. So we get products of manifolds that admit metrics of non-negative sectional curvature with a product metric. We get homogeneous spaces, D mod H with a bi-invariant metric on G. All of those admit metrics of non-negative sectional curvature. And a little bit more general, the biquotients, also all of them except the metric of non-negative sectional curvature. And more examples, we can look at connected sums of any two rank 1 symmetric spaces. So that's a result by Jeff Cheeger. They all admitted, in general, sphere bundles over S4. That's a result by Kova and Siller. And then more recently, all exotic 7 spheres. So all of them except such a metric, and that's a result by Goethe, Karen, and Shankar. So this is sort of the difference between the positive and non-negative sectional curvature. We do know many more topological obstructions in non-negative sectional curvature, but we also know a lot more examples. Now, in general, if you want a general classification, so a topological classification, that's a very difficult problem. And one approach to the problem has been to add some symmetries. So let me review some of the known results. So adding symmetries, meaning we now, in addition to the assumptions we have on positive sectional curvature, we also want to assume that we have an effective isometric circle action, T1 action. And so this is in dimension 4, so you can ask this problem, of course, the question in general. But if we look at dimension 4, if you assume such an action, then Xiang and Kleiner showed about many years ago, almost 30 years ago, that the manifold can only be an S4 or a CP2. So in dimension 4, with this additional symmetry, you can only get those two cases. And why doing that? So the reason one introduced this, to look at symmetries is because a lot of the examples one knows have a lot of symmetries. So the original classification here was by homeomorphism, and then improved to, in fact, equivariant diffeomorphism by Curvature and Curvature. So I have a lot of these people in the audience today. So okay, so that was dimension 4. And if you now weaken the condition on the sectional curvature to non-negative, there's a corresponding result by Kleiner and Searle-Yang. So again, compact, simply connected manifold, non-negative curvature with an isometric effective T1 action. Then in addition to the S4 and CP2, you also pick up S2 cross S2 and CP2 connected some plus or minus CP2. So that's the CP2 with the opposite orientation. And again, it was a homeomorphism classification that was then improved to equivariant diffeomorphism by Galas-Garcia and Curvature. So that's dimension 4. So we have a very good idea what happens in dimension 4, get a very nice classification. For higher dimensions, and this is what I was going to mention, there's the maximal symmetry rank theorem that states that if you now start with a general N manifold, positively curved, and you assume you have an isometric TK action, then what Kurve and Searle proved is that you get an upper bound on the torus that can act. So the TK here, the K, can be at most about half the dimension of the manifold. So that's n plus 1 over 2, the floor of n plus 1 over 2. So you get a restriction on the torus, and if you reach that maximal dimension, then your manifold is diffeomorphic to a sphere, a CPN, and then you also pick up an RPN and a length space because we did not assume simply connected here. So, and again, that result was improved, in fact, to equivariant diffeomorphism by Galas-Garcia. So we have a very nice result for positive sectional curvature. Now, if you want to weaken this to non-negative, all we have is a conjecture. So the conjecture here is same setup. We have a closed, simply connected, now non-negatively curved manifold with an isometric TK action. We again get a bound on the torus. This time it's larger, it's 2n over 3. And the claim is that if you reach the maximal dimension, then your manifold is equivariantly diffeomorphic to a product of odd and even dimensional spheres, or the quotient of such a product by a free linear torus action of rank. And now this is shorthand notation, it's 2n mod 3. So that means it's either a T1 or a T2. So you have in that maximal dimension, you have a very restrictive setting. And because this is all shorthand notation here, I wanted to show you what it looks like. So if you actually go through and you look at the various possibilities, and I wrote it out by divisibility by 3, so the dimension n is by divisibility by 3, And that's just because, our bound here is 2n/3, the floor of 2n/3. And if you now also think about the maximal symmetry rank of the torus on the individual spheres, and if you look at the various dimensions, all you can get in the case that the dimension is divisible by 3, you can just get a product of 3 spheres. What I didn't mention before is that you have to have at least a 3 sphere there. So you can't have S1s. So you get m copies of S3. If you go to -1 mod 3, you pick up an additional S5, or you could have a product of 3 spheres divided by a circle. And then if you go to -2 mod 3, you pick up either an S7, an S4, or you could be a product of 3 spheres divided by T2, or the S5 cross the S3s by a T1. And that's it. So it's quite rigid in the maximal symmetry rank. But all of that is a conjecture. And I want to tell you a little bit about the history. So what do we know about this conjecture? It's well known in dimensions 2 and 3. It's known in dimensions 4, 5, and 6. And there was first a diffeomorphism classification by Gallos, Garcia, and Searle in 2011, and then improved to equivariant diffeomorphism by Gallos, Garcia, and Karen in 2014. Okay, so let me see. Yeah, so let me go back. So in attacking this problem, one thing one can do is instead of requiring, so we have this isometric TK action, but we now want to also see what kind of isotropy groups we can have. And so there are further restrictions we want to impose on the action, and that is of an isotropy-maximal or almost isotropy-maximal action. So here's the definition. So if we have a TK action, and this is just in general, so you can define this in general, so it doesn't have to be an isometric action, so just a smooth action on a manifold, Mn, we call it isotropy-maximal if there is a point such that the dimension of its isotropy group is maximal. So the largest isotropy you could have for such a TK action is n minus k. And if you have a point that has that isotropy group, we call it isotropy-maximal. Okay. And then almost if you have 1 dimension less. That's the definition. And you can immediately translate that into the orbits. So a TK action is isotropy-maximal if and only if you have a point where the orbit is TK mod Tn minus k, so you get an orbit of dimension 2k minus n, or 2k minus n plus 1 in the almost isotropy-maximal case. And I will give some examples in a second. We also want to distinguish, so it turns out, so isotropy-maximal actions are always almost isotropy-maximal, so we want to distinguish those that are just almost isotropy-maximal, and we call those strictly almost isotropy-maximal. And so that means 2k minus n plus 1 is the smallest dimension of any orbit. So there is no smaller dimensional orbit. And just to note here, because we're going to see this later, it turns out for a strictly almost isotropy-maximal action, because you have now an orbit of dimension 2k minus n plus 1, that means the smallest orbit is of odd codimension in that case. Okay. Good. Okay, so here's some examples. So for an isotropy-maximal action, so remember the dimension of the smallest orbit is 2k minus n. So if I assume that 2k minus n is 0, so I have fixed points, then I get a TK action on twice-dimension manifold with fixed points. And those manifolds are torus manifolds, so that's a definition of a torus manifold. And they are very well studied. So there are lots of nice results about torus manifolds. And here's a simple example. You could have a T2 on S3, just where you act on each component. Smallest orbit here is an S1, and that matches. That's a 2k minus n is 1. So those are isotropy-maximal actions. For strictly almost isotropy-maximal, if I do a similar thing, I look at the smallest orbit, which is 2k minus n plus 1. If I want that to be 0-dimensional, then I get a tk acting on an odd, so on m2k plus 1 with fixed points. And those are also sometimes called odd torus manifolds. So those are the analog of a torus manifold, which is always even-dimensional in odd dimensions. And here's another example. If I have T3, say, acting on S3 cross S3, where on the first S3, I just act as above, and on the second S3, I don't do anything on the first component, has again smallest orbit in S1, and 2k minus n plus 1 is indeed 1. So those are all isotropy or strictly almost isotropy-maximal actions. How about examples? How about non-examples? So what is not isotropy-maximal? So if you look at the definition of the minimum orbit, again, 2k minus n was the dimension of the smallest orbit. So in particular, that means it has to be bigger or equal to 0. So that gives you a bound. So if I take a tk on mn, where k is in fact less than n over 2, or less than n minus 1 over 2, that can never be isotropy-maximal or almost isotropy-maximal. So if you want small torus actions, right? So if you're less than half the dimension, they will not be isotropy-maximal or almost isotropy-maximal. Okay. So I want to first write down or present the theorem for isotropy-maximal actions. So what Catherine and I proved is that if you assume that you have a simply connected manifold with non-negative sectional curvature and an isometric now isotropy-maximal. So I put now the condition isotropy-maximal on the tk action. Then in that setting, we get an upper bound for the k, for the torus. We get a lower bound too. That's, again, just from what I explained, it has to be, the minimum orbit has to be bigger or equal to 0, the dimension. And we show that m in that case has to be always equivalently diffeomorphic to a free linear quotient of this Zm, which is, again, a product of even and odd dimensional spheres by a torus. What I want to point out here is that looks very much like the maximal symmetry rank conjecture, but the maximal symmetry rank conjecture only said that if you reach the top dimension, the maximal dimension, then you have this classification. This says it's always the case. So if you have an isotropy or almost isotropy-maximal action, the manifold always will look like that. And typically, your torus can be, the torus you divide by can be larger than just the T1 or the T2. So you will have other cases coming up. And there are various applications. So of course, that shows that if I restrict myself to isotropy-maximal actions, the conjecture holds, right? The maximal symmetry rank conjecture, because it definitely holds in the top dimension. What we also proved is that if you have a homogeneity 3 action, so if you have now, I wrote it here as Tn on Mn plus 3, so the orbit space is 3-dimensional and a manifold of non-negative sectional curvature, then we showed that that action always has to be isotropy-maximal. So that means that we can push, so this was for n bigger or equal to 7, we can push the maximal symmetry rank conjecture now without any assumptions on the isotropy subgroups to dimensions 7, 8, and 9. Okay, so this is homogeneity 3. And we also show that the conjecture in fact holds for rationally elliptic manifolds So if the Butt conjecture is true, namely that non-negative sectional curvature implies rational elliptic, then it does hold. So, but the Butt conjecture is very difficult conjecture. So, so that would imply it. Okay, any questions? Okay, so let me state the main result that I want to talk about. So I want to weaken this the condition of isotropy-maximal to strictly almost isotropy-maximal. So the claim is that you again get a bound on K, and you get a very similar statement. So again, we claim the manifold is equivalently diffeomorphic to a free linear quotient of a product of even and odd dimensional spheres by a torus. Okay. And this is just a general, it's just a comment. So I wanted to point out that if you're going back to a positive section curvature and n even, then there are no such actions. So Berger's result implies that for even dimensional manifolds, positively curved, you have to have a fixed point, but that means the codimension of your minimal orbit set must be even. But for strictly isotropy-maximal actions, it always has to be odd. So these can never be strictly isotropy-maximal in the positive setting. So that's also a nice, I mean, a difference between the positive and the non-negative setting. Okay. So I want to talk about some tools for the proof. So I want to outline the proof, but I need some tools that we used. And the first tool is the notion of a locally standard action. That is a tool we use quite a bit. And I define it here first for torus manifolds. So a Tn on M2n, we call this action locally standard. If it's locally modeled on the standard action of Tn on Cn, and what that means is that around each point on the manifold, you can find a T invariant neighborhood that is what's called weakly equivalently diffeomorphic to an open subset of Cn. And what the weakly here means that it's equivariant up to an automorphism of the torus. So if there is an automorphism of the torus and a diffeomorphism that satisfies f of ty is not t, but phi of t, f of y for all t and tn. And the action on the w is just the standard action. It's a strong condition, but it turns out that we can prove in our case you do have such actions. And I also want to state a little bit more general definition of locally standard, which means that, again, for any point on the manifold, there is a neighborhood such that u now is tk equivalently diffeomorphic to the product of tk minus I here is the dimension of the isotropy subgroup at the point x, cross w2i, and then a remaining rn minus k minus and W, so W again is just an open subset of Ci, and with a standard Ti action, and then I have trivia actions, Tk on Rn minus K minus I, and Tk minus I on W, and the isotropy subgroup on Tk minus I. So it's a specific neighborhood of your points. That's what it means to be locally standard. Okay. I also need Spindeler's nice decomposition result. So I now want to focus on fixed point homogeneous group actions. So this is in general, if I have a group acting on a manifold, we call it fixed point homogeneous. If it's up there, so the dimension of the orbit space minus the dimension of the fixed point set is equal to 1. So in general, the dimension of the orbit space is bounded below by the dimension of the fixed point set for transitive actions. So if you reach that lower bound, then you call it fixed point homogeneous. And it turns out that for our actions, so for these isotropy-maximal or almost isotropy-maximal TK actions, there always is a circle sitting in the TK that acts fixed point homogeneously on the manifold. And so we're in a setting where we can apply Spindeler. So there's a very nice result that we certainly use all the time by Spindeler, where if you have a manifold with non-negative sectional curvature and such a nice fixed point homogeneous G action, and if F is a fixed point component, so a component of the fixed point set of maximal dimension, then he showed that there must be a G invariant submanifold N at maximal distance from F of M without boundary, such that you can write your manifold as a disk bundle over F union a disk bundle over N glued together along their common boundary. And the is here is an equivariant diffeomorphism. So that's a very nice result. And I will mention this later. The way we use the result is the proof technique. So the way we prove this result is, and also the previous result, is through induction on the dimension of the orbit space. And so the idea here is, if we know that our manifold decomposes like this, both F and N will be manifolds of smaller dimensions, and in fact, they will have a lower cohomogeneity. So we can apply our induction hypothesis and put everything together to get the result for M. So this is very heavily used for both proofs. Okay, so I also want to just mention the two other theorems we use here is the Cheeger-Como splitting theorem, which says the main part we need here is that if you have a compact, non-negatively curved manifold, then the universal cover of the manifold splits isometrically as compact manifold cross an RK. So we can always know what the universal cover of such a manifold is. And we will need this. Let me go back. When you think about it, so I said we're going to use Spindeler to as an for our inductive argument. Our assumptions are always that the manifold is simply connected, but in general, F and N will not be. So that means we have to use some knowledge about the cover of these manifolds. Well, we're also going to use Predon's lifting theorem, which says that if you have a connected Lie group that acts effectively on the manifold, and now I look at any covering space of M, then there is a covering group of G with an effective action cover on M prime covering that action. So in particular, if you have finitely many sheets of M prime, then you get the same for G prime sitting over G. And if G has a fixed point in the manifold downstairs in M, then in fact the two groups have to be the same. So G prime is equal to G, and the fixed point set of M prime is the full inverse image of the fixed point set of M. So those two we will need. So here's the outline of the proof and the setup. So our setup is always, we assume non-negative curvature, isometric, strictly almost isotropy-maximal TK action. And the first result we have, and we will definitely use this quite heavily, is that in such a setting, you can actually extend the TK action to a smooth TK plus 1 action that is locally standard and isotropy-maximal. So we start with an isometric TK that is strictly almost isotropy-maximal. We show that we can extend it to a TK plus 1 that is both locally standard and isotropy-maximal. And moreover, and this will also be important if I look at the orbit space of that smooth action, so the Mn mod the TK plus 1, then it is diffeomorphic to a disk, and all of its faces are. And this is after smoothing the corners. So these orbit spaces are what's called nice manifolds with corners, but after smoothing the corners, they will be diffeomorphic to disks. Okay. So this is what I just said earlier, right? The proof of this result also will be an inductive argument on the cohomogeneity of the action. So the dimension of the orbit space using Spindeler and I will write this down in a second, careful case-by-case analysis, and the fact that these two, so what one can prove from this nice decomposition of Spindeler, you just use a Van Kampen type result to show that these fundamental groups of F and N have to be cyclic groups. Okay, so our proof now will be divided into cases of either finite or infinite cyclic. Okay, so if we have and I wrote M here, but this will be for our F and N from the decomposition. So if we have finite cyclic group, then if we go to the universal cover, what we get is, and this is using Bredon, right? We get a closed, simply connected, non-negatively curved manifold, now with an isometric, strictly almost isotropy-maximal TK action. So we have to lift the action up, and we get such a TK action. And in the infinite cyclic group case, we again have this splitting, and in this case, I think the R here is probably not correct. So we get an M bar across R to the, should be like a power of R, and M bar is a closed, simply connected, non-negatively curved manifold with an isotropy-maximal TK action. So it could be either isotropy-maximal or a strictly almost isotropic-maximal TK-1 action. And that's because it depends on the lift of your group. So the group could be, because it's infinite cyclic, right? It could be either the same, or it could be one dimension lower across R. Those are the two possibilities. And so you have to argue, you pretty much argue these two cases using both the splitting theorem and the lifting theorem. Okay, so that's how you prove. So that was for the proof of the extension of the action. Once you have this extended action, so we now have an isotropy-maximal TK+1 action on Mn, which you remember is smooth. So it's not an isometric action. So I have a smooth action, but it's isotropy-maximal. So that means I now have an isotropy subgroup of the largest isotropy subgroup is n minus k minus 1, right? Because I have a k+1 acting on Mn. So that means I get a torus, right? I get if I subtract that, so my TK+1, and I subtract the isotropy subgroup, I get a torus, a subtorus that's acting almost freely on the manifold. Okay. Now that's great because we can divide by that, right? We have our manifold and we can divide by this almost freely acting torus. We get, if the action is free, we would get a manifold, right? We would get a manifold of dimension 2n minus 2k minus 2. If it's not free, then we get an orbifold. So, but the end result is we get a closed, simply connected orbifold with an induced Tn minus k minus 1 action with a fixed point. So we take our manifold, we divide by this almost freely acting torus, we get an orbifold with a fixed point, but those are called torus orbifolds, right? So remember, if it's a manifold, it would be an even dimension manifold with a half dimension torus acting with a fixed point. Those are called torus manifolds. So this is a torus orbifold. And you will see in a second why that's great. So what we also show, and again, using inductive argument, that if the TK action is strictly almost isotropy-maximal, then the manifold itself must be rationally elliptic. And if I have a rationally elliptic manifold and I divide by a torus action, the result will be rationally elliptic. So the space X here is a rationally elliptic torus orbifold. And the great thing is that once we have a rationally elliptic torus orbifold, we know exactly what the orbit space looks like. So the orbit space of such a rationally elliptic torus orbifold, so I wrote it down again, our Mn mod Tk plus 1, so that's just the orbifold divided by half-dimension torus acting. The orbit space here is just a product of simplices and what we call lunar suspensions of simplices. So the deltas here, those are just Sn odd-dimension sphere divided by a Tn I plus 1. That's just a simplex, a standard simplex. And the sigmas are just suspensions of simplices where you then remove the simplex that you suspended by. So these are suspensions of simplices. And we know that from a result by Gauss, Garcia, Karen, Radesky, and Wiemler. So what they showed is that these type of rationally elliptic orbifolds, their orbit space is always combinatorially equivalent to such a nice space, nice polytope. And then using Davis, you actually get that it's a diffeomorphism, so always up to smoothing the corners, if the quotient space and all of its faces are diffeomorphic to disks. And that's exactly what we had in our result. So we proved, right, that this extension, not only can we extend, but we also know that the action is isotropy-maximal, but also the orbit space is diffeomorphic to a disk, and all of its faces are diffeomorphic to a disk. And that's why we can apply Davis to show that we actually get a diffeomorphism there. Okay. And let me go back. So this setup where you have your manifold, you have a locally standard action, you go down to an orbit space that looks exactly like that. That's exactly the setup for the tools we proved in the isotropy-maximal case. And so in order to tell you a little bit about how you can complete this argument now, I want to talk about these moment angle manifolds. So turns out if you have these nice polytopes, then there's always associated to each polytope a moment angle manifold. So sitting over each polytope, you have these particular nice manifolds, and I will give you the definition, but one has to show that it's actually a smooth manifold. It's not clear from just looking at the definition. So here's the definition. So for each point in the polytope, so in Pn, this is a technical term here. We want to denote S of Q, the set of those facets of the polytope that contain the point Q. So facets here are just codimension 1 faces of the polytope. And then for any simple polytope with M facets, you define this manifold as the product of M facets. So I look at a Tm cross the polytope modulo equivalence relation. So it's just the product of this torus that is determined by the number of facets of the polytope and the polytope itself, where you identify 2 points, T1P and T2Q, if and only if P is equal to Q. So you don't do anything on the polytope, but T1, T2 inverse is in the torus that is just the product of the S1i's, where those are determined depending on how many facets of Pn you have that contain the original Q. And just to give you a baby example of this, because it's kind of hard to follow, let's look at the 1 simplex. Yes? Yes and no. There are various constructions, but that is one of the standard constructions. There is another equivalent construction of those. Yeah. I find this easier to digest, so that's why I gave this one. So, but there is, yeah, it is in the toric varieties. That's one of the terminologies from there, yeah. So let me look at a one simplex, right? I have an interval. So that means I have two facets, right? I have two endpoints. Those are my codimension 1 faces. So that means I get a 2 torus. So I get T2 cross I modulo the equivalence relation. And now let's look at what happens if you're in the interior of this interval. Then there are no facets that contain that point. So in the interior, there are no identifications. So you just have a torus on the interior. If you get to the endpoints, then you have one facet that contains it. So you have sitting over the endpoints a circle. But that's just the join of two S1s, which is S3. So the moment angle manifold of a one simplex is a S3. And this is in general, so you can generalize that. It turns out that the moment angle, and you're right, so it's complex. They usually use complex. So you can show that in this setting, though, it is a manifold. So these moment angle manifolds of simplices.
So sorry. When do you know under what conditions on your P this will be a manifold?
So I wrote the definition down for a simple polytope, but you can generalize it a little bit. So it works for the also for the you have to look at these nice manifolds with corners. So you can generalize it. It holds for a little bit more general class than just simple polytopes. It's just you know you can say that again. No, it's like a simplex is a simple polytope. So it will have, you know, it's.
The one scale is the complete graph. Every vertex.
Oh, the simple part, yeah. Yeah.
So you will say it again? It's a complete graph. So one scale is every vertex is connected to every other vertex. So that is continuous. So I assume.
Yeah, no, that's correct. So, so it turns out that for simplices, you always get odd-dimensional spheres. So this is in general in higher dimensions, and for the suspensions of simplices, you end up with even-dimensional spheres. So the manifold. So when you remember the orbit space, right? The manifolds that we got, they all come from moment angle manifolds. They're all products of odd and even dimensional spheres. Okay, so so we can now use our machinery. So from the Isotropy-Maximal classification, I'm way too fast. I'm going to finish early. So so here's what it is. So in general, if we have, so our Mn is up there, right? And then we have a locally standard Tk plus 1 action to this orbit space, Pn minus k minus 1. What we showed in the Isotropy-Maximal classification is that whenever you have such a locally standard action with this type of polytope, you can find a section. So we construct a section, and once you have a section, so you can look at first the result for homeomorphism, right? Using the section now, you can show that the manifold Mn then is homeomorphic to a moment angle manifold if and only if you have a weight preserving homeomorphism between P and P bar. And weight preserving here means that it will send weights to weights, right? So you actually have to define this homeomorphism, not just on the polytope, but also on the weights of the isotropy subgroups that are attached to the faces. And to get it to diffeomorphism, you have to use the fact that the action is locally standard again to show that you can find not just a continuous section, but also a section that's regular enough for you to extend it. So the result for diffeomorphism is once you have a rate preserving diffeomorphism on the orbit spaces, you don't get an if and only if. So you get a diffeomorphism between the manifold and the moment angle manifold. But that's all we wanted to show here, is that you get a diffeomorphism between your manifold and the moment angle manifold. Now, the picture I wrote is just for the case where you get that the manifold is just a product of spheres, even in odd-dimensional spheres. But remember, the statement said it's actually that or a quotient of that by a free linear torus action. And so it turns out for some of the cases, and that depends on whether the number of facets of your polytope is equal to the dimension of the torus that's acting. And if it is, you get immediately just a moment angle manifold. If it's not, it turns out that sitting over this manifold is another manifold that with a principal bundle over it. And we know that what's sitting over it will be, and that's a torus bundle, so it will be diffeomorphic to a moment angle manifold, so that your original manifold is the quotient of the moment angle manifold by a free linear torus action. So, but the point is that once you're in this setting that you have a locally standard action that gets you all the way down to an orbit space that you know, then our machinery works and you get the classification just as you did before. So the extension result is really what finishes the proof, is that you have an extended action that gets you down to the same setting. And I'm done.
So thank you very much for the beautiful talk. Are there questions or remarks?
Are there results that if you have bounds on the Betti numbers, say 2 to the n over 2?
So they get bounds on the Betti number?
If you have a bound on the total Betti number, say 2 to the n over 2, that's the number you would expect, that then you can get the almost, what's it called, maximal symmetry rank conjecture. I mean, somehow you would think that if you have such a torus, and it would freely say that the Betti numbers are big.
That would give you a bound on the Betti numbers?
A lower bound on the Betti numbers, yeah.
I don't know.
Okay.
My co-author? Interesting, I don't know. Yeah, no, I don't know.
Further questions?
As you can tell, there are lots of open questions still. This is only a partial answer to the problem.
Okay.
Any idea how to proceed from?
I can tell you what would be nice. So our next step here is actually to look at. So if you remember, when I looked at the conjecture and what we proved in the Isotropy-Maximal case, how we got to the conjecture for these cases 7, 8, and 9, we used the fact that cohomogeneity 3 action was always Isotropy-Maximal. So we're looking at cohomogeneity 4, what can happen there, and it's much more complicated. So cohomogeneity 4 would be sort of the next step to see what happens if the orbit space is 4-dimensional instead of 3-dimensional. But there seem to be many more cases that can come up. That is also, yeah, that is also